Welcome back. This is video lecture 26.3, and we have one more topic to discuss in chapter 26. And we're looking specifically in section 5, where we're going to talk about the concept of power in electric circuits. Now, last semester, we did talk about the concept of power, so that's not brand new to us. The symbol was capital P. And it was first defined to us as the rate at which work is done. All right, rate, derivative, work, W. Okay? Remember, work is transfer of energy between a system and its surroundings by means of a force. So we talk about work, we've got a force, we've got a displacement, that's work. We're talking about the rate at which work is done, dW dt. Later on in mechanics, we also broadened our discussion of power a little bit more to be not only the rate at which work is being done, but also just the rate at which energy is being transferred between a system and its surroundings, or the rate at which energy is being transformed from one form to another. And so in that sense, it's often more broadly written as dE dt, the rate at which energy is being transformed or transferred. Note again, the unit would be joule per second, which is called, if you recall, its own unit, the watt. Well, certainly, as we will discover in electric circuits, we have energy being transferred and transformed throughout the circuit. And so we often want to keep track of that rate at which the energy is being transferred or transformed in a circuit. And how do we do that is the point. So I'm going to tell you how we do that. I'm going to try to be very careful about explaining it because it's very fundamental to understanding electric circuits, and show you the simple formula for calculating the power associated with a circuit element in a circuit. So let's look at my first picture here. Now, it's a schematic representation of a device in a circuit, often called a circuit element. I've just drawn it as a kind of a rectangular box because it stands generically for anything that could be in a circuit. And it has been connected up through conducting wires to the rest of a circuit, which I'm not showing, but it is a complete circuit. And we have current I flowing into this device on the left, and the same current I flowing out on the right. Always remember, current cannot just disappear in a device. It has to go through, okay? And I'm going to think of this current as conventional current, which means that it is due to the motion of positive charges. So when I show a little arrow pointing to the right and label it I, that means I'm to think of positive charges are flowing through the conductor, and then through the device, the conducting wire on the left, and then through the device, and then through the conducting wire on the right, and onward. Okay? And I is the rate at which that positive charge is passing through a point, dq dt. Okay, so again, this is just part of a complete circuit, and we're focusing on this device. We're also going to hook up a voltmeter. You've used those in labs. And that's going to measure the potential difference, V, between the two ends of the device. And in my first picture, the way this device is operated is that as the conventional current flows through it from left to right, the left end has the higher potential, and the right end has the lower potential. To say it another way, as the current flows through the device from left to right, the potential drops. Okay? This is a potential drop. Because the potential is less at the right end than it is at the left end. The potential is less at the end where the current comes out compared to the end where the current goes in. Okay? All right, so what that means is that my positive charges in my conventional current as a positive charge that's part of the current moves from the left end to the right end, it has a drop in potential energy. Okay? So the current, in some sense, is losing energy. Where's that energy going? Into the device. Okay? The device is gaining energy at the expense of the energy from the current. That's one important point. We always want to keep track of which way is energy being transferred in a circuit. And there are basically only two options. When you've got a device with current flowing through, the direction of energy transfer can be either into the device from the current or the other way, which I'll talk about in a minute. But right now, the energy is flowing into the device from the current. If you want an example of what such a device might be, probably the most common example would be a plain old vanilla resistor. Vanilla here just meaning common. Okay? A plain old circuit element called a resistor, which was designed to have a certain amount of resistance in ohms. Whenever you put a resistor as a device in a circuit, and current I is flowing through it, then the current will always flow from high potential to low potential through a resistor. The resistor will always gain energy from the current, and that energy will show up in the resistor in the form of thermal energy. Resistors get hot when you run current through them. Now, it depends on how big the resistance is and how big the current is as to how hot it's going to get. It may not be terribly hot, or it may be very hot. And like an example of that second case would be any kind of technological device you're used to that uses thermal energy in a heated resistor, like a hairdryer, or a toaster oven. Okay? Now, another possibility is that the device is a battery that is a rechargeable battery, and it is being recharged. We are transferring energy from the current into the battery itself to recharge it. Okay, so that's an example of a situation where I have a device that's gaining energy from the current. And that's always going to be true when, in the device, the current flows from higher potential to lower potential. Now, this formula that I have gives me one other important fact. Okay, so let's read this bulleted statement. If we have current I traveling through a device from high to low potential, and so we have a potential drop by some amount V, then energy is transferred from the current to the device. That's worth emphasizing. The direction of the energy transfer is from the current to the device. And here's the rate at which that energy transfer happens. In other words, power. P. It's merely the product of the current I going through the device and the potential drop or difference across it. Now, I want to show you very briefly where that formula comes from, because it's very simple and it's very useful in circuits, and we will use it constantly. And people just say P equals IV. All right, let's imagine a cross-section, a mathematical surface, slicing through the device somewhere, like that, okay? And then we know the current through that cross-section is I. It's got to be the same I as in the wires. Current can't just disappear. And that's equal to the rate at which charge is passing through that cross-section, dq over dt. And the way we think about that is that an amount of charge dq crosses through the cross-section in a tiny time interval dt. And now let me just take that and rearrange that formula and write it as dq equals I times dt. All right, now, here's another idea. So that's one idea. Let me put a little bullet by that. Here's another idea. I'll just continue down here in this space. As one of my little amounts of charge dq which I'm thinking of as having positive charge, remember conventional current, flows from left to right through the device, how much does its energy change? Okay. All right, so as dq moves from left end to right end, it'll have an energy change du, because it's potential energy that's changing. And just from the definition of electric potential, that's going to be the charge that moved, dq, times the potential difference it moved across, which is just v. I'm going to write it then like this. V times dq. That's really just from the definition of potential as potential energy per unit charge. All right, now let me replace that dq part with I times dt from the first comment. And then let me divide both sides by dt. So I get du dt is v times I, and then I just identify du dt as being equivalent to the dE dt. It's the rate at which energy is being transformed out of the potential energy form. So that is exactly what we mean by power. And so then we have this very useful general formula for the power associated with any circuit element, absolutely any circuit element. Because I made no assumption about what that circuit element in that box was. You just take the product of two things, the current I flowing through the device and the potential difference V across it. Okay? P equals IV. Now the units, of course, just think about that a minute. The unit of current, you should know now, is the ampere. And the unit of potential difference, of course, is the volt. Let's think about those units a little bit. Volt is joule per coulomb. We need to remember that. Ampere is coulomb per second. We need to remember that. Multiply those units. The coulombs cancel. You have joule per second, which is watt, which is correct. Okay. So far, so good? Definitely remember this formula. And that we have to be able to keep track of which way the energy transfer is going. In our top picture, the energy is being transferred from the current to the device. Now I want to look at this lower picture. Still a device in a closed circuit with current, conventional current I, motion of positive charges, flowing in the left end of the device and out the right end. And I've got my voltmeter across it measuring the potential difference V. But now my voltmeter tells me that the right end has the higher potential than the left. Okay, so now what we have is the current I is traveling through the device from low to high potential. In other words, it's a potential gain, V. So the positive charges in the conventional current, as they move from left to right, are gaining energy. In other words, energy is transferred from the device to the current. That's the direction of the energy transfer. It's still at the rate P equals IV. But it can happen this way too. So the direction of the energy transfer can be from the device to the current. The device can be giving energy to the current. An example here, and this will be very common, is a plain old vanilla discharging battery. A battery that's giving up some of its stored energy, probably in the form of chemical potential energy, to the energy of the current. Okay? So it can happen that way too. And we do need to keep track, as I said, of which way the energy transfer is happening. And this is P equals IV is valid for any circuit element of any kind. Now, what if, special case, what if the device is a resistor with a known amount of resistance R in ohms? Then we can simply combine the general power formula, P equals IV, with the definition of resistance, R equals V over I. Okay, so let me draw a picture down here. Again, part of a complete circuit. Conventional current I is flowing in from the left. Now my device, which before I was just drawing as a kind of a mysterious box with current I flowing out, is now a resistor. Let me show you the circuit diagram symbol for a resistor. It's just an up and down zigzag, and you put an R by it, meaning that's its resistance. And the left end is the high potential side, and the right end is the low potential side, and the current is flowing from high potential to low. It's a potential drop, V. And so we are transferring energy from the current into the resistor, into thermal energy of the resistor, at the rate P equals IV. And that's certainly true, right there. But I can take the definition of resistance, R equals V over I, and I can solve it for V. V equals I times R, and substitute that right there for the V, and I get another expression for power that can be useful. I squared times R. Take the current going through the resistor, square it, and multiply it by the resistance in ohms. Useful if I know I and R. What if I don't know I? But what if I do know is the potential difference V? We'll then go back to the P equals IV formula and using the definition of resistance, but now solve it for I. I equals V over R. And substitute it in there for the I. And then you get just another version of the power expression, V squared over R. So they all say the same thing, but note, these last two forms here are only if the circuit element is a resistor with a certain amount of resistance. And resistors always take energy from the current. They never give energy to the current. Okay? They always take energy from the current and convert it into thermal energy. Okay, so we'll just close with a class engagement exercise for Blackboard that just involves practicing with P equals IV, which can be expressed as I squared over R, which can be expressed as V squared over R if your object is a resistor. So here's the scenario. We have a potential difference V across a device with resistance R. That means it's a resistor, causing current I through the device. And we're going to make some changes, and we're going to ask us to think about how the power has changed. So here's what it says. Rank the following variations according to the change in the rate at which electrical energy is converted to thermal energy due to the resistance. Now watch out, that's code. Rate at which electrical energy is converted to thermal energy. Power. Okay? Due to the resistance. Okay, so we have some initial power, which is just I times V, or I squared times R, or V squared times over R, excuse me. That's our initial situation. If you like, P sub I, where the I means initial. And then we're going to get, with these four cases here, with each one, we're going to get a P final. Okay? And I basically want to see how the P final compares to the P initial, and then I want to be able to rank those P finals amongst these four. Which of these four has the biggest P final compared to P initial? Which of these four has the next biggest P final, and the next biggest P final, and the smallest P final? And here are the changes we're going to make. One by one. Case A. We double the potential difference, and we don't change the resistance. Now don't worry about how you would go about doing this in the circuit. just take these cases. Okay, case A, double the potential difference V, but don't change the resistance. Case B, double the current I, but don't change the resistance. Case C, double the resistance, but don't change the potential difference. And case D, double the resistance, but don't change the current. So in each one of those, I want you to find an expression for P final in terms of this P initial for each one, and then rank those P finals from biggest to smallest. Okay? That's our task. And then we will be talking in class about power for circuit elements in electric circuits. And that's all for this video.